Okay, now we will go over the 3 by 3 case. It's similar to the 2 by 2 case. However, we need to obtain 3 solutions, not just one. Okay? And so, well, if the eigenvalue has multiplicity 3. So, for instance, suppose we are given this as our system, then just by looking at it, you can figure out that the eigenvalue is 2, or you can, of course, compute the characteristic polynomial. And so, well, we can find one solution, x1, that's of this form, and this will just be the eigenvector. And so let's compute it. So this will be 0, 1, 6, 0, 0, 5, and 0, 0, 0. So v1, v2, v3 is equal to 0, 0, 0. Okay, and so if you notice, this is v2 plus 6 v3 equals 0, and 5 v3 equals 0. v1 is free. But if v3 is 0, then v2 is 0, which means that v1 is free. So, let's just let that be 1 because we don't want that to be 0. Okay, and so x1 is going to be e to the 2t 1, 0, 0. Okay, so this gives us one solution. So now we need another solution. And so we make a guess, like last time, that it's going to be of the form e to the 2t w plus t e to the 2t v. Okay, and last time we did this abstractly, so the same matrix equation should hold, namely a minus 2i, where a is this, v equals 0, and a minus 2i, and w equals v. Okay, and so v is the eigenvector, which we already compute, and w is this generalized eigenvector, which we can compute by setting up the eigenvalue equation, but instead of saying that this is 0, we set that as v. And so we want to solve for w. Oops. That satisfies this 1, 0, 0. So this corresponds to v2 plus 6 v3 equals 1, and 5, w3 is equal to 0, and w1 is free again. So w1, w2, w3 again is 0. If w3 is 0, w2 is 1. w1 is free. Since this is non-zero, we can set the free variable to be 0, so that it's not the 0 vector. And so this gives us our second solution, right, by just plugging these into this formula. And so now we need a third solution. And so you can basically play the same game and guess that it's going to be of the form e to the 2tz plus t e to the 2tw plus t squared over 2 e to the 2tv. Now you might be wondering why we divide by 2. You don't have to, but if you do the same derivation, then having this 2 comes in handy because it cancels out with a 2 that, when you take the derivative, it'll cancel out with here. In any case, if you set it up like this, then the corresponding matrix equation will end up being a minus, it'll be a minus 2iv is equal to 0, and then a minus 2iw is equal to v, and then a minus 2i of z is equal to w. So now you just take the vector that you computed last time and put it there, and then you compute your z. So in this case, it will be 0, 1, 6, 0, 0, 5, 0, 0, 0, and z1, z2, z3 is equal to 0, 1, 0. Okay, and then it's the similar equations. So it's going to be z2 plus 6z3 is equal to 0, and z5, z3 is 1, and then z1 is free again. So this generalized eigenvector, z3 is 1/5. If z3 is 1 over 5, then z2 will be negative 6 over 5. And z1 is free, so we let that be 0. Okay? And so now we plug all these in so that our general solution will be x equals c1 times x1 plus c2 times x2 plus c3 times x3, where c1 x1 was e to the 2t 100 plus c2 x2 was our second solution, which was e to the 2t 010 plus t e to the 2t 100 plus c3, c3 times what we just computed, which was e to the 2t times z, which is 0, negative 6/5, 1/5, plus t e to the 2t 010 plus t squared over 2 e to the 2t of 100. Okay. And so that is what we do when we have multiplicity 3. Okay. So now, kind of an interesting variant is what to do if your system is, say, 2, 1, 0, 0, 2, 0, and 0, 0, 2. X prime equals x. Well, there's kind of two ways to think about it. You can actually just write everything out. So this will be x1 prime equals 2x1 plus x2, and x2 prime is 2x2, and then x3 prime is 2x3. So actually, like, this x3 is kind of independent. So this is really, you just kind of solve this two-dimensional system and this one-dimensional system separately. So you can do that. Or in this linear algebra method, right, let's compute the eigenvectors. We have 0, so lambda equals 2 by observation. And then if you subtract 2 from the diagonal, you get something like this. And so this time, it looks like we'll have, oops, oh man, these are bad choices. Let's see, v1, v2, v3. So this time, it looks like we're going to have 3 free variables because the only requirement is v2 is equal to 0. Everything else is just 0 equals 0. And so v1, v2, v3 can be split into v1 times 1, 0, 0 plus v3 times 0, 0, 1. And so you have 2 linearly independent eigenvectors. And so one of our solutions is e to the 2t times 1, 0, 0. Another solution is e to the 2t times 0, 0, 1. And then x3. So how do we compute x3? Is you just apply kind of the same method, but with this guy. So so then you compute the generalized eigenvector. I mean, what I mean is, so it's going to be of the form e to the 2t w plus t e to the 2t and v, and we want to solve for a minus 2i v equals 0 and a minus 2i w equals 0. However, something bad should happen if we use the wrong vector. So let's just try. This is the wrong way to do it, but let's see. So if we have 0, 1, 0, 0, 0, 0, 0, 0, 0, and then we want to solve for w1, w2, w3, and we set this equal to an eigenvector. If we set this as 0, 0, 1, something terrible should happen. Namely, we have w2 equals 0, and that's it. So then you just end up with the same. So then you end up with the same two eigenvectors, right? And so those aren't linearly independent. That's bad, right? But if you instead make this 0 and make this 1, so you pick this one, then you get w2 equals 1 and everything else is free. And so your generalized eigenvector is going to be 0, 1, 0, and so you can plug it into here with this v, and then you get your third solution, which would match up if you had done this separately. I mean, so this example, it's easy to see which solutions and vectors correspond to which ones. Okay.